properties is different in between discrete time and continuous time complex exponentials. Discrete time complex exponential with the frequency omega naught plus 2 pi, that is e power j of omega naught plus 2 pi of n equal to e power j 2 pi n e power j omega naught n. We multiply j omega and n here. J 2 pi n equal to j power e power j omega naught n, e power j omega naught n. From equation 1.51 we see that the exponential frequency omega naught plus 2 pi is same as the frequency at the frequency in omega naught. Frequency in omega naught plus 2 pi same here in omega naught also. Frequency both are same here. We have different situation from the continuous time case in which the signal is e power j omega naught t are all distinct for distinct values are all actually here all are distinct values of omega naught. In discrete time this is not a distinct all as the signal frequency omega naught is identical to the signals with the frequency omega naught plus or minus 2 pi, omega naught plus or minus 4 pi, and so on. Therefore, in considering discrete time complex exponentials, we need only consider a frequency interval of length 2 pi in which to choose omega naught. Although according to equations 1.51, any interval length 2 pi will do. On most occasions we will use interval 0 to 2 pi. Omega naught in between 0 to 2 pi, or the interval omega naught in between minus pi to plus pi. From the equation 1.51, the signal e power j omega naught does not have continuously increasing rate of oscillation as omega naught is increased in magnitude. That is, omega naught is increased in magnitude, but that oscillation rate is not increasing. Signal e power j omega naught does not have the continuously increase the rate of oscillations. Oscillation is not increasing, but omega naught is increased in magnitude. Rather, in figure, as we increase omega naught from 0 to pi 2 pi, continuously increasing, which produces same constant sequence as omega naught equal to 0. The rate of oscillations always decreases. Actually, omega naught increases from 0 to pi 2 pi like that, but the rate of oscillations decreases until we reach 2 pi. Actually that cycle is only 2 pi only, minus pi to plus pi, or 0 to 2 pi, that's all, which produces same constant sequence as omega naught 0 equal to 0. Therefore, the low frequency, that is slowly varying discrete time exponentials, have values omega naught near 0 to 2 pi, and any other event multiplier by of pi, while the high frequencies corresponding to repeat variations are located near omega naught equal to plus or minus pi, and other odd multiplies of pi. Note in particular that for omega not equal to pi or any other odd multiple of pi, e power j omega e power j pi n equal to e power j pi power n equal to minus 1 power n. So that the signal oscillates remedially changing sign at each point in time. In figure 1.27, that is here in E, first positive 1, then positive negative 1, positive 1, remedially changing. That's why here mentioning. So that signals remedially changing sign at each point in time. The second property we wish to consider concerns the periodicity of discrete time complex exponentials. Discrete time complex exponential. In order for the signal e power j omega not n to be periodic with period n is greater than 0, we must have e power j omega not n of omega naught of n small n plus capital N uppercase n equal to e power j omega naught n. Equivalently, e power j omega naught n equal to 1 or 1.4 equation to hold omega naught n must be multiple of 2 pi. That is, there must be an integer m such that omega naught n equal to 2 pi m, or equivalently omega naught 2 by equal to m divided n. According to equations 1.5, the signal e power j omega naught n is periodic if omega naught divided by 2 by is rational number. If omega naught divided by 2 by is not a rational number, the signal e power j omega naught is not a periodic. The same observations also hold for discrete time sinusoids. For example, the same observations hold for discrete time sinusoids. For example, the signals depicted in 1.25 figure A and B are periodic, while the signal in figure 1.25C is not. In this figure A, signal is periodic. In this figure B, signal is periodic. Here is not periodic. C is not periodic. We can also determine the fundamental period frequency of discrete time complex exponentials, where we define the fundamental frequency of a discrete time period signals as we did in continuous time. That is, if x of n is periodic with fundamental period n, its fundamental frequency is 2 pi n. Consider then a periodic complex exponential x of n equal to e power j omega naught n with omega not equal to 0. As we have just seen, omega naught must satisfy the equation 1.56 for some pair. Okay, for some pair of integers m and n with n is greater than 0. In problem 1.35 it is shown that if omega naught is not equal to 0 and if n and m have no factors in common, then for the fundamental period of x of n is n. Using uppercase n. Using this fact together with the equation 1.56, we find that the fundamental frequency of the periodic signal e power j omega naught n is 2 pi divided by n equal to omega naught divided by m. The fundamental frequency of the periodic signal e for j omega naught n is 2 pi divided by n equal to omega naught divided by m. Fundamental periodic n also written as n equal to uppercase n equal to small m into 2 pi divided by omega naught. Note that the fundamental period can also be written as n equal to m of 2 by divide omega naught. These last two expressions again differ from their continuous time counterparts. In table 1.1, we have summarized some of differences between the continuous time signals e power j omega naught t and the discrete time signal e power j omega naught n. Note that if continuous time case, the constant discrete time signal resulting from setting omega naught equal to 0 has a fundamental frequency is 0 and the fundamental period is undefined. Once I note that a continuous time case, the constant discrete time signal resulting from setting omega naught equal to 0 as fundamental frequency of 0 and its fundamental period is undefined. Comparison of signals e power j omega naught t and e power j omega naught n, that is these continuous time signals, these discrete time signals. So in continuous time signals, periodic signals, yeah, actually the discrete time resulting omega naught is 0, fundamental frequency also 0, fundamental period is undefined. This is a very important point. Here, distinct in continuous time signal under distinct signals for distinct value of omega naught, distinct signals for discrete value of omega naught. Here in discrete time signal e power j omega naught n, identical signals for these values of omega naught separated by multiples of 2 pi. Identical signals for values of omega naught separated by multiple of 2 pi. Periodic for any choice of omega naught, periodic only if omega naught equal to 2 pi m divided by n for some integers n greater than 0 and m. Fundamental frequency omega naught, fundamental frequency omega naught divided by m. Here fundamental period omega naught equal to 0, undefined, omega naught equal to 0, 2 by divided omega naught. Fundamental period omega naught equal to 0, undefined, omega naught is not equal to 0 m of 2 by omega naught assumes that m and n do not have any factors in common. Gain some additional insight into these properties. To gain some additional insight into these properties, let us examine again the signals depicted in figure 1.25. First, consider the sequence of x of n equal to cos of 2 pi n divided by 12 depicted in figure 1.25a, which we can think of these set of samples of the continuous time sinusoid x of t equal to 2 pi cos of 2 pi t divided by 12 at the integer time points. To gain some additional insight into these properties, let us examine again the signals depicted in 1.25. First, consider sequence x of n equal to cos 2 pi n divided by 12 depicted in figure 1.25a, which is we can think of as the set of samples of the continuous time sinusoid x of t equal to 2 pi t divided by 12 at the integer term points. In this case, X of t is periodic with fundamental